שלום לכולם, ברוכים הבאים למפגש שלנו בנושא AI וסייבר. Welcome everyone to our session about AI and cyber. This is going to be frontal and virtual. So for the viewers, you're a part of the show as well. We welcome you here and welcome you to ask questions and participate. I'd like to invite our keynote session manager, Major General Professor Itzik Ben Israel, the conference chairman for Cyber Week, to give his keynote.
Good morning. First, let me welcome you to Tel Aviv University. It's, I think, number 11 conference that we do. Perhaps we skipped one in 2020 because of the corona. But next year it will be as it was before. I mean, with some 10,000 people roaming through this campus. And I would be grateful if you come again next year. Now for this session, I mean, the subject is cyber and AI. And in a way, it has two vectors here. One, how cyber influences AI, and the other one, the other way around. AI influences cyber technology. It's not so simple as it sounds. One vector is simple, maybe. The Israel National Cyber Directorate is using cyber AI technology for years now in order to detect anomalies to guard our networks, communication networks. The idea is very simple and it's used since 2015, I think, or 16. If you want to secure the network, you look at the bits running from one node to another node, and these bits carry perhaps innocent information or sometimes malware, viruses, and you need to find a way to understand if it is malware, then you have to do something against it. If it's not, you should allow it to flow through the network. But the classical way of doing it is to decode the bits, look at the content, and if it has some signature of a malware, then you do something. If not, you ignore it. But by doing it, you harm the privacy of people. You have here a kind of tension between security on one hand, which is important, and privacy, human rights of our own citizens. I'm not speaking about enemy or bad guy or something like this on the other hand. And therefore, AI can offer here a solution. You put a machine, a computer that will look at the bits without going to the level of content, without decoding them. And then sometimes you may say that the behavior of this series of bits is suspicious as a malware, without going to the content. If you study the traffic and detect anomalies, and this can be done only by machine learning technology, human beings cannot really follow all the data running. So this is obvious, a connection between AI and cyber security. But you know that in this area, technology is not standing still. It's running faster than anyone can even follow. And the bad guys that understood that some people are using machine learning in order to protect their networks devised ways to learn how this machine learning protection is working and to deceive the algorithms of machine learning. I mean, any intelligence can be deceived. If I would like that you not to recognize myself, I would put a wig on my head, shave my beard, something that I didn't do since I was 18 years old, and things like this. this will work on your brain, and many times I can hide my real face and prevent you from identifying me. The same can happen with artificial intelligence. I mean, if you know how the algorithms of that determine the identity are working, you can change a little bit the picture, a little bit. I mean, with our brain, normal brain, we will not even detect the difference between the modified picture and the original one, but it will be enough for the machine, the algorithms of machine learning to be deceived. And then if you use this, you can overcome the technology that I spoke a minute ago about, and still go back to the cyber business. Now you, as a security, I mean, like as people who are in charge of security, we have to find a way to answer this, and this will go forever. By the way, the same technology that was developed here to work against the protection of AI on communication in networks, same technology can also work for our benefit, not only for the bad guys to overcome the protection of AI machines. I'll give you one example. I guess many of you tried to look for and use Google to look for pictures, and my picture is stored in so many social networks, data storage of individuals, of organizations, etc. If you want to know something about me, you can do a Google search on photos and find a lot of information about me, and by this, my privacy will be hurt to a certain extent. Now, if you use the technology that I've just described and change a little bit the pictures stored in every storage in such a way that for our eyes, you still be not affected and look at the picture and see me, but for the machine who is looking at the picture, it will look like a different picture. Then if you try to use Google search and find all the pictures of me, you will fail. So the same technology, it's a kind of dual use technology. Same technology can be used also for our benefit and not only by the bad guys. The AI also is really what, I mean, is one aspect, the development of AI is one aspect of computer technology, which is the dominant technology of our age. And cyber technology, I mean, and the more dominant technology, computer technology becomes, the more vulnerable we are becoming to cyber attacks. So these are two different sides of the same technology. And therefore, whoever who wants to be effective in cyber protection, cyber security, or to develop new cyber technologies must go to the next step, and this is the AI step. And that's why the Prime Minister, the outgoing Prime Minister, Netanyahu, appointed Professor Aviatar Matania, who used to be the head of INCD, and me in 2018, 3 years ago, to submit to the government a program, a plan, how to make Israel one of the top 5 countries in the world within 5 years in AI. And we are still waiting for a solid government with a budget, something that we didn't have in the last 2-3 years, before we can implement the plan. And we wait for this. I hope we will have it. And the idea is that the next step should be towards AI, not only in cybersecurity. Cybersecurity is only one of the aspects of it. And I saw here Udi from the INCD, who was in charge of the team, who led the team wrote a report on this aspect of cybersecurity and AI. And I guess once we will have a government and a budget, we will meet you again, but this time to speak about AI as the next step. Thank you very much.
Thank you, Itzik. I wanted to use this opportunity to share with you the think process that we did in INCD regarding AI and cyber. Since I have a very limited time, it's going to be very fast, so try to keep up. This is an AI is interesting technology because, as Itzik said, it's of dual use. We need from one side to protect it, from the other side we can use it to protect other stuff. Some of the things we touch are similar, and some of the things we just need to protect. First challenge we had is deciding if it's cyber. It sounds weird, but we have to think about it specifically. Some domains are a bit tricky. Think about deep fake for influence on social. This is less cyber, but today we're going to use videos, real live testing for biometrics. So deep fakes there all of a sudden become something different. What we did basically is try to divide it into several categories of interest and address each of them. First one was the obvious one, how to use AI for defense. After we took a look at the landscape and saw that pretty much this is something the industry is doing rather well on itself. We just don't need to interrupt. So we went to the next step and thought about how to defend against an AI attacker. This is something that we see today as a work in progress. So mostly today we see a kind of evolution in specific techniques like text translation, voice manipulation, deepfake. We don't see it a really smart orchestrated attack, but for sure this is coming. So looking forward, we probably need to use some kind of an AI-based mechanism to protect ourselves against an AI attacker. Third topic is the most obvious one. How do we protect the AI itself? Surprisingly enough, it's not on the mainstream of most of the companies that produce AI models and use AI for their own purpose. They don't spend that as much time on making sure that it's a protected domain. So starting from traditional attacks like DDoS on AI or things like that, dataset poisoning, which is outside the domain of the model itself, but it's important. There are a lot of areas where we need to deploy protection. We as the INCD, as a kind of a regulator to the cyber domain, looking into this and try to understand how we can help setting some kind of standards, providing best of breed and so forth. It raises the natural questions, trust and visibility. How can you trust something that you don't understand? You don't know how it works. You don't have the source code to look back and examine it. And in some cases, the system is constantly evolving. Think about rating systems or recommendation engine. They keep evolving as long as the more data you feed them, they change. So you can manipulate them by manipulating the data itself. Smart automation is one domain that we are focused on as well. We think about this today in the more respect of kind of boutique tasks. So think about red tape, IR teams, or reversers. These are high-profile occupations that are very hard to generate, they're very hard to produce. And this is if this is domain where we can use AI to solve some of these challenges, then it's a very interesting domain. The data layer protection. Today, when we talk about data protection, we talk about mostly data in transit and data in rest. But interesting enough, we have a lot of those PEC, the privacy enhancing cryptography, such as homomorphic encryption and so forth, that give us the benefit or the ability to keep data encrypted all the times. And this opens up for us a whole range of interesting applications, starting from enhancing security. So not only keep the system, but protect the data as well. And it allows us to lower the bar in some areas with respect to things that you can move out. Now, it's not up to us. The trend of moving out off premises everywhere. The government is, just released a tender for Nimbus, which is a government cloud, a public cloud. This is the way people work. It's less on-premise and more out there. And the issue is not only confidential information, army-like, is sensitive information, think medical information. So things that we can move out and enjoy the power that resides outside, it's for our benefit. We're actually doing an experiment of this with the medical data, but I wouldn't go into this. Last topic that I'm going to mention, I'm not sure that all of you know, but the secured biometric unit is part of the INCD, and they're doing quite a lot of work on the AI and biometrics. With respect to adversarial, impersonating people online and offline, the deep fake, the domain of using guns to generate data in the domain where it's very difficult to get data legally for this. And we come across a lot of interesting issues up to the fact of one interesting research that we did, that we saw, about what AI can tell from your face. So it's not only specific biometric things, but like cameras in the public space, but it's also things that we need to regulate. So Endgame, what are we doing? We're working in several fronts. We're working with Academy to generate research and promote research in areas that we think that are worthwhile. We have our own R&D program together with DoD R&D, where we have several ongoing projects in the domains I mentioned, encrypting AI, protecting AI, both on software and the hardware level. We are deploying a kind of regulation, something like TOAG, the Torat Hagana, which is a document from INCD stating the best of breed practice of how to do stuff. So we're going to generate a version that has adapted controls for AI, and this is going to be, of course, an evolving work. And we're working very hard in the international perspective, since we think that the problem is worldwide and we can benefit from working with partners. We have several such cooperations with different governments. That's it. I welcome questions, and anyone wants to not now, after the, sorry. If anyone has an idea or wants to pitch in for something, we're open. Thank you. Sorry. And I'm welcoming Nimrod from Big ID. We actually met. I told him a couple of years ago when I was working in the Ministry of Justice, and I saw his product there, and it's going to be very interesting to hear about the progress.
I don't see that. Thank you.
All right. Hi, everybody. Can you hear me? Okay. Nice to see everyone. My name is Nimrod Vax. I'm a co-founder of Big ID. Big ID is a data intelligence platform that kind of scans organizational networks for data, builds a catalog of the data, and provides ways to take action on the data, an application tier that allows you to use the data to protect privacy, use the data to protect the data itself, and use that data intelligence also to govern the data. That's kind of a high level. The topic I chose to speak to you about today is probably a topic that would have been more well received at the end of these presentations. as you see some of the threats around AI, and whether there is a need to regulate AI, and which is an initiative that the European Union is starting to push forward with a solidified kind of regulation proposal that is coming this year for debate, and maybe kind of brought out in the next year or two. Very similar to the GDPR, if people are familiar with which is the General Data Protection Regulation that the EU has put out about 3 years ago. So, you know, we've kind of become almost indifferent to all of those cameras that are around us and the surveillance, both online and in the streets, right? We're being monitored by the government. We're being monitored by merchants. We're being monitored by our neighbors, right? All of this data is being collected and is readily available for analysis, typically AI-driven analysis. So, you know, we can't avoid the feeling that we're being watched, right? And even though it's been, 30 years since or so since 1984, we are even in a worse situation than what Orwell described in his book. But it's not really about the creepy feeling, right? It's not really only about privacy. There's a very serious consequences to this type of analysis and to possible mistakes. I don't know if any of you have heard about the UK post office scandal. Apparently, and this is not directly related to AI, but it really it's an indication of what how our reliance on technology can lead. Because of a bug in a ERP system that the UK Post Office introduced in the late 90s, this bug basically caused the post office to wrongfully indict 80 people and put them in jail for accusations of fraud. These people were completely innocent, but were still served months in jail. One of them even committed suicide. And this all is an indication of what our reliance and trust in software can lead to if it's not regulated or even follows some kind of trust. And if you think about the AI systems that we put in place, they are even more obscure than the software that we have been used to in the past few decades. Also, there can be other consequences, right, for AI failing, right? We all heard about the accidents that happen here and there. Now, it doesn't mean that AI is less secure than a driver, obviously, but it does mean that if there is a fault, especially when we apply AI in very critical processes, it becomes very, very dangerous, or it could be very dangerous. Also, our ability to process huge amounts of data. The technological progress in social media is putting this technology in the hands of governments and other organizations, and for not so much, very, I would say, enlightened purposes, right? So China is putting in place a credit system, a social credit system. That, on the surface, it's legitimate, right? To see who is trustworthy to take a loan, right? What is his credit score? The US has this system for decades. But really, the ability to process huge amounts of data here using AI really allows the Chinese government to monitor each and every one of its citizens at a very granular level, not only about their financial activities, but also their social activities, what they do. Are they jaywalking, right? Each one of those little pieces of information goes into that system. And suddenly, if something goes wrong, or even if it doesn't go wrong, not only that you cannot get a loan, you can't get a job, you can't rent a house. So the consequences are really significant. So these are some of the use cases of why in the EU, every problem is solved by a rule or a regulation. So there is that proposal in place to really protect and monitor and make sure that the software and the AI procedures that we put in place are really up to par in terms of quality and are not being misused for illegitimate uses. So the EU has some definition, and you can see the definition of what is AI is very broad. Right, it even includes Bayesian estimations, which cause a little bit of, and it might change, but it really talks about supervised, unsupervised learning, knowledge graphs, and knowledge bases, and things of that nature that we would categorize as AI. I think between the people here, and this regulation proposal really suggests a risk-based approach. This risk-based approach is not talking about the type of data that you're processing. It's not talking about the methods that you're putting in place. It really talks about what is the purpose of this AI. What are you trying to do? What are you trying to achieve? So at the bottom, and that's where most of the AI activities that happen today rely, we're talking about very kind of day-to-day type of activities, chatbots and spam filters and things of that nature. That is probably more than 80% of the AI activity going on in the market today, and this is left mostly unregulated, just with a moral code of conduct of how to use this information. At the higher level, where there is limited risk, we're really looking at more advanced technologies like deepfake, like emotion recognition. That are used for different purposes in commerce and so forth. And there is a request for transparency. There is a request, especially if you talk about things like deepfake or chatbots that you communicate with support chatbots or sales chatbots. You want to know that you're talking with a chatbot and not with a human or the other way around. So there is a requirement for transparency that you would know as a human that you are not talking to a human, so that you know how to deal with it and you know how to operate it. Also, it requires transparency on how the algorithm works, so you know how to avoid pitfalls, etc. Where it really gets more interesting is in the high risk and the unacceptable risk that the EU is defining. And again, the high risk definition is really about what is the purpose of processing. When we're talking about high risk, we're talking about high risk activities like using AI for machinery, using AI for cybersecurity, using AI for even for migration purposes. When you go into a country and monitoring, and you could be banned from entering a country just because of some kind of an AI algorithm. Biometric identification and categorization. I don't know if you know that, but you could be categorized and you could be identified just by the way you move, the distinctive way you move, how you drag a foot, or how you move your hands. You could be categorized based on your race just by looking at a picture. So these are activities that are considered high risk, and there should be a good justification for using AI for these purposes. So there are a set of requirements that need to be maintained under this new regulation in order to be compliant, right? First and foremost, know your data. That's the number one kind of requirement. Make sure that you have high quality data, that you're using the right data set. It's not polluted. It doesn't have a lot of noise in it, that it's coming and it's legitimate. And this is, by the way, not new. The financial sector is required by law to show data quality and to show the quality and the lineage of the AI algorithms that are being used for reporting and for decision making and for trading for many years. But now this is becoming a broader requirement, not only for financial services. Transparency, right? Show the users let them know they're using an automated AI system, not a human. It's important, but also be transparent about the algorithm itself. What data sets did you use? These data sets need to be available, need to be able to monitor and reproduce those data sets. Be transparent about what the decisions, the predictions, understanding one of the biggest problems in AI, I'll talk about it at the end, is how do you explain the decision? How do you explain a confidence score that you received from an AI system? You need to be able to do that. You need to be able to trace back and provide that visibility. You need to show the intent, the purpose of processing. This is also remember, the purpose of processing is really what defines the risk. And you need to be transparent about it. Why are you using, what are you using this for? As an end user, you need to know what the AI is, real purpose is. The other aspect is, I think most of the conversations here will talk about is keeping it secure and safe. Being able to protect the data sets, protect your system from being hacked, making sure it's accurate, and being able to communicate if there is a hack, have some fail-safe procedures in your system. What happens if you discover that there is that you cannot rely on the AI model? You need to have fail-safe functions, and you need to do your best to prevent cybersecurity attacks. It's very similar to the privacy regulation, where you are obligated as a data processor to protect the data, right? And that's a very important aspect. There are some additional requirements like human oversight and traceability and auditability, documentation of what you're building. And really this regulation is very similar to the stamp of kind of quality. It is actually the stamp of quality for AI systems. It is a self-assessment, so it shouldn't add a lot of overhead. It's not something you need to submit to a third party and wait 3 months for them to approve it. But you need to prove that you've done due diligence, and if you are audited, you need to be able to show that. So it falls under that same mechanism that the EU has for years already. What is unacceptable risk? There are purposes of processing that are defined as illegitimate by the EU. Social scoring, for example. Dark pattern AI, which is understanding or trying to understand emotions or subconscious behavior and leveraging that. One of the examples that were given is that driving or causing truck drivers to be able to drive longer hours by using some kind of noises or things like that. Manipulation of feelings, and also real-time biometrics. So that scanning, those cameras that we see, a lot of restrictions on that by law enforcement. So it's very limited to law enforcement use. You need to receive a pre-approval to use this data and to monitor. Very similar to what you need to provide in a court of law. And the penalties are very high, higher even than the GDPR penalties. So we're talking about 6% of the total revenue if you violate the unacceptable risk, and very similar to the GDPR on the other limitations. So I didn't want to just kind of bum you down with regulation without giving some kind of a way out. And what are the, what is a framework for compliance? What can you do as a vendor that's developing AI or a researcher in order to comply with those regulations with minimum effort? Obviously we are offering some of the capabilities that we see and we are able to offer as well, but not only us, there are other vendors in the market, obviously, that perform some of this. It's really about data, right? AI is about data. So know your data. It starts with discovery and understanding the data, understanding the quality of the data, adding the right context to the data. So you know also what is the data used for, what type of data it is, finding the high quality data you want to use. That allows you to trust that data and be able to build reliable AI mechanisms that you can then govern and maintain. Keep documentation, and if you start and you have the ability to document the ability or or document the traceability of the data, be able to have that interaction, both automated kind of lineage, but also be able to interact with the users, with the data scientists that are using this or building this machine learning model, so that you document the purpose of processing, you document where the data is coming from, and you document who you are sharing this data with or this model with, right? So we're moving from a model where, or an environment where you document and catalog your data set, to a situation where you catalog your AI models. An AI model is almost like a big table that you have in your environment that you need to document. You need to document where the data came from, what is the lineage of that table, so to speak, who is using it, what is the purpose of processing, and so forth. And explainability, one of the cool features we've added recently, by the way, is the ability to trace and explain a confidence score that we use in the product to show the confidence of the discovery or capability or classification of the data, and be able to explain why an attribute received the confidence score. What were the significant features that impacted that confidence score that you could change? And how do you change those features in order to mitigate or either reduce or increase the confidence score? So that's kind of a quick overview of this. This is kind of an overview of what BigID provides, connecting to the data, knowing the data through cataloging, classification, correlation, and cluster analysis, and then taking action on the data using an application framework that you can use on top of it. Any questions?
One question for you, Nimrod. Why do you think AI is different from other software? Do you think we need to regulate all software?
So I think that the AI, it's really like the difference between a knife and a gun, right? AI brings so much capabilities that you need to have more control, and it's used so broadly in it's so critical environments that the cost of a mistake is too high, right? So just the saying that you don't need to have a license for a knife, but you need a license for a gun is kind of, I think, the right metaphor to explain that. I hope that. Okay. Any other question?
Has AI increased the cyber attack surface?
Every component you introduce to your environment increases the surface of attack, and yes, I think that most of the lectures that you will hear today, the sessions that you will hear today, will talk about how this attack surface can be leveraged. Absolutely.
Major concern.
Thank you very much.
All right. Thank you.
Thank you, Nimrod. I'd like to invite Liron David, a researcher from Tel Aviv University.
Okay, hi everyone. Thank you. I'm very delighted to be here. I'm going to talk about passwords, and I'm going to show you a system that can estimate the strength of a password using some learning process. But before I'm going to start, I have some question I would like to ask you. It's regarding passwords, of your choosing of your password. So when you need to choose your password and you are asked to have at least one capital letter. So how many of you choose the first letter of your password to capitalize this letter? Yeah, okay. Now, when you choose your password, you're also required to have at least one symbol, which is one special character. Now, how many of you choose the exclamation mark as your special character and put it at the end of your password? Yeah, okay. And another question, how many of you use your personal information inside your password? Okay. your name, your family name, your children, birthday, and so on. Okay. Okay. So I'm going to use it and I'm going to show you that actually you're not the only person who's going to do that. Actually, most of the people do exactly what we've seen now. So we're talking about password. So of course it's important to have a strong password for all our profile, whether it's for our Facebook, bank account, eBay, LinkedIn, and so on. But the question is, what does it mean a strong password, right? We all want strong password, but what does it mean a strong password? So a strong password, like generally talking, is the one that cannot be easily cracked using brute force attack. So in order to achieve strong password, most of the website actually forces the user to have at least one capital letter, at least one lowercase, at least one digit, symbol, and at least 10 characters in total. However, this policy does not necessarily guarantee you a strong password. And why? So let's assume we have the following password, which is New York 12, and then the exclamation mark. So as we've seen, and also you said, most of the people actually capitalize the first letter of your password, and then they add the 12 at the end, and then they put the exclamation mark at the end. So the cracker, actually, they're well familiar with this behavior. So they can crack this password very, very fast, although this password actually meets all the requirements, which is capital letter, lowercase, digit, symbol, and 10 characters. So this is not a strong password, although it meets the requirements. Therefore, what we need is to have a better password range estimator. And this is what we did. So this is where our algorithm comes in. So what we did is we developed an online password range estimator, and by we mean me and Professor Avishai Wool. This is a joint work with Professor Avishai Wool, and this system called PESRank. And how does it work? So this system actually learns the common password people tend to do and the common transformation people tend to do, going over a huge corpus of leaked password that we can find on the internet. And then given a new password, our system can say how strong the password is. So how are we going to do that? So we consider 5 transformation most of the people tend to do. So first of all, they start with some base word. This is like the base password, let's say password. And then what most of the people do, they add some digits and some symbols before this base word, before this password. And we call this transformation the prefix transformation. Then what they do, they add maybe another symbols and digits, maybe also after the password, also after the base word. And we call this transformation suffix. Another transformation people tend to do and need to do is the capitalization. So they choose one or maybe more letters to capitalize this letter. And another transformation people tend to do is the lit transformation. Lit transformation is replacing a letter by a symbol or digit, which looks like this letter. For example, we replace the A by the @ sign, which look similar to each other. Okay, so this is the 5 transformation we actually notice that people tend to do. And what we're going to do is we are going to go over a huge corpus of leaked password from the internet. We can freely download this from the internet. And then we learn all the common values of each transformation. So after the learning phase, we actually have 5 lists. And we have all the prefixes people tend to do, all the base word people tend to choose, all the suffixes they tend to choose, the capitalization pattern they tend to do, and all the lead transformation they tend to do. Then after we have these 5 lists, we actually go over these lists and we calculate the probability of each unique item in this list. And then we sort these lists in decreasing order from the highest to the least. So this was the learning phase. Now we're moving on to the estimation phase. So in the estimation phase, first of all, let's define what is a password in our system. So a password in our system is actually a combination of a prefix, base word, suffix, capitalization, and lit. Now this is a password in our model. Now, what is the probability of this password? So the probability of this password is actually the multiplication of the probabilities of its part. So if the probability of the prefix is Q1 and the probability of the base word is Q2 and of the suffix is Q3 and the capitalization Q4 and so on, the probability of the full password is going to be the multiplication of these 5 probabilities. Okay, now that we understand what is the probability of a password in our model, what we wanted to have is wanted to have a sorted list of all the possible passwords in this model, of course, sorted in decreasing order from the highest to the least, and this would have had the optimal order of password for the crack to try. Now, given a password, how does it help us? Given a password, if we find its position in this list, we actually find the number of attempts a cracker needs to do until it finds this password. So our goal, by the way, we denote this position by the notation rank. So our goal is to find, given a password, we would like to find its rank in this list of all the passwords sorted from the highest to the least. And then, generally speaking, how does it help us? If we receive a password that has a high rank, it means that this is a strong password. Why? Because the cracker will not reach this password in a feasible time. However, if the rank is low, so this is a weak password. Why? Because the cracker will reach this password in a feasible time. So having this list is actually very nice, but the problem is that we cannot generate this list from two reasons. First of all, we cannot generate it in advance and then store it because of space consuming. And we cannot also generate it on the fly for any password because this will be time consuming and this is a prohibit. So what we did in our algorithm is we developed a new algorithm that calls ESRank. This is an efficient algorithm, and what this algorithm can do, it can given the probability of a password, it can approximate its rank in this list within the factor of 2. However, without generating this list, therefore it works in fractions of second. So how does it work? Given that we have our password, what we're going to do is we're going to find its transformation, and then we're going to find the probability of each transformation. Then we're going to multiply all the probabilities of all its parts to have the probability of the password. And then given this probability, what we do, we just apply the algorithm that we've developed that calls ESRank. And given this probability, it just returns back the rank of the password, which has this probability in the huge list, although we are not generated. And this happens actually very, very fast. This algorithm is very, very fast. As we can see, the average estimation time per password is very, very low. If we train our system on 33 million passwords, it takes only 0.024, which is very, very fast. And even if we train our model on 900 million passwords, it will be very, very fast. The average will be 0.033. Okay, so far we've seen how to estimate a password that all its transformations exist in the list. But what happens if we receive a password such that one of the transformations does not exist in the list? Let's assume this transformation and this suffix, and let's assume that this suffix does not exist in the list. So in that case, what we do is we are looking at the lowest probability in the corresponding list, which is the suffix, and then we take the lowest and we multiply it by some factor alpha, and this is going to be the probability of the unknown suffix. And then we, as before, we just multiply all these 5 values and we receive the probability and we apply the algorithm as before. And this is what we call the unleaked smoothing mode. Okay, so now let's compare our algorithm with other methods. So there exists some other method who try to model the behavior of crackers, and we're going to compare ourselves to these 5 methods, which is the Markov model, the PCFG, the Hashcat, the John the Ripper, and the neural network base of Melicher. And as we can see, there are 2 graphs. On the left, we compare ourselves to the Hashcat, PCFG, Markov, and John the Ripper, and on the right, we compare ourselves to the neural network base of Melicher. And these 2 graphs show the accuracy of the model. So the highest is the line. It means that the model is more accurate. And we are the black line, also on the left and on the right. So as you can see, our model is actually more accurate than the models that we compare to. The dashed line, by the way, are the point in which the smoothing mode is insert, and we chose alpha to be 10 to the power of -3. We also compare the training time of our method with other methods. So the PCFG and the model, when they train on 41 million passwords, so it takes for them days. while for our algorithm, it takes only 12 minutes, which is, of course, much, much faster. And also on a bigger amount of password, when the neural network, they train themselves on 130 million passwords, it takes days. And for our system, it takes only 35 minutes. Again, very, very fast. Another two advantages of our algorithm is that first, it can be personalized. So as I ask you, and most of the people actually tend to use their personal information in their password, again, because it will be easier for them to remember this password. So, and by personal information, I mean name, first name, last name, children name, ID, birthday, and so on. And so this is very common behavior of people. So our algorithm, the PES1, can actually accurate estimate the cracker how many attempts he's going to do, given that he knows the personal information of the user. So how we're going to do it? It's very easy. So assume that we know the personal information. All what we do is going to the corresponding list, and we just push this information up to the top of the list. So if, for example, we know the personal information Adam, so all what we need to do is just to increase the probability, which means to push it to the top of the list. And this modification takes only fractions of seconds, and of course, without the need to retrain the model. Therefore, it's very, very useful. And the second advantage of our algorithm is that it can be explainable. Okay, it can explain why we received this rank, and it can give some insight of how to improve your password. And this is, of course, in contrast to some superior method and especially those who based on the neural network, which inherently cannot explain their results. And okay, so let me just conclude. We proposed a novel password strength estimator called PES-Rank, and this model accurately models the behavior of a powerful cracker, and this is practical for online use, and the training time of this model is much shorter than the exist method, and it can be personalized without being retraining again, and it can be explainable. And this paper was accepted to the Zurich 2021 conference, and we are going to present it in October in Germany. So thank you very much for your attention, and I would love to take your questions. Yes.
I think I have a question that pretty much everybody has.
Yeah.
Where can I access it?
Okay, so now, so this model, yeah, so actually this model, as you can see, this is an algorithm, but of course we also showed you that we implement this algorithm, and we actually use this algorithm. We integrated this system in a course at Tel Aviv University, a course that Professor Avishai Wool teach, and we integrated twice in the registration page of this course. We integrated twice, this year and last year, and actually people tried it. I mean, the students, when they register, they try this model, and we receive very good feedback, and they actually improve their password, make it stronger, and so we actually we implement it and we use it, and we yeah. You personally. So you will be able to use it when we will come out with this product, like in the future. Yeah. So we're actually working on this. So yeah.
Thank you.
Okay. Thank you very much.
Thank you, Liron. I'm sure many people here are running home to change their password. I'd like to welcome Professor Ernesto Damiani. He's a professor at the Department of Informatics, University of Milan. He's going to join us online.
Wonderful. Thank you very much. And I hope you're also seeing I'm sharing my slides, so I hope that you can also see my slides. So I will start. There is the computer science department in Milan, and the work that we've been doing here on this topic and the subject I'm going to speak of is being developed in collaboration with the Institute for Intelligent Systems, and specifically the Center for Cyber Physical Systems at Khalifa University in the UAE that you see on the left-hand side of the slide. And we have a flagship project, which is a flagship project on how to weather cyber storms, specifically targeting machine learning, and specifically targeting machine learning applied to a number of verticals, which are of interest for the UAE. I don't want to go too much into the details of the application. Let me say just a few words. When you apply machine learning to cybersecurity data, well, you basically tend to follow the classic life cycle of getting samples of a certain label, the sample somehow. For example, in malware identification, this is for malware detection type of application. You have malware behavior encoded somehow, and of course in a vectorized form. You have to label the behavior, and then once based on the label, you're going to train a system, and you hope that the system, which has learned from the examples, will also be in production capable of distinguishing malware from a benign software application. So this is, I mean, what I would say that the straightforward type of application of ML techniques, and we have been hearing a lot of promises. So now this artificial intelligence type of approach would sort of improve the capability of some cybersecurity type of applications. Well, there is a problem we know very well, because we've been, this problem has been facing it when trying to train antiviruses, or trying to train a number of cybersecurity type of application, which is the time you require to update. For example, when a new malware is released, and you have to sample the behavior of the new malware to add it to the known samples, and then retrain your malware detector. So this is basically a periodic retraining problem. And we are not sure that we can be fast enough and good enough. And also we are not really sure of the level of immunization that you get from, the model which has been trained only on known examples, where a new malware has its 0 day and starts spreading in the system, in the network. So basically, there have been a lot of interest in being able to generate behavioral models that basically could apply to a number of malwares, even the malwares which have not been released yet. And in this way, to be able to counter the notion of periodic retraining with continuous shaping and plasticity of your machine learning model. So this is something that, again, it's been debated a lot, and we are trying to put this in production as we speak. To bring this type of protection in production, so being able to use a machine learning model to counter threat, you need also to make that model robust. So if you use a model which is going to basically identify malware, what you need to do is also to make sure that the malware is not affecting the model that you are trying to use, in order to decapacitate that model from its own capability of detection. And so you need to make the training of that model robust. And robust training is a problem for machine learning models. One technique that you can do is to try to turn a single monolithic model into an ensemble and try to make the ensemble more robust than the original monolithic model used to be. And another technique that you can use is, once you have released the model into production, again, this is a model for detecting, for example, hostile behavior on the part of applications, you may want to try to make that model checkable with other models deployed around it in a distributed fashion, in order to be able to heal it, just in case someone is interfering with the model plasticity in production. So you see, we have to, when we want to deploy machine learning, we need to make it effective. We need to make it its training timely. We need to make it robust in training, and we need to make it robust during the inference phase when it is deployed in production. So you see, we have these 4 concerns that we need to address. And we have, of course, adversaries which are trying to make our 4 goals elusive. They are trying, and they are basically doing so, at least from the literature, we have the idea that they are doing so by crafting examples that can be used in the training phase or can be used in the phase in production. And those examples are crafted in such a way to either compromise the training or compromise the model once it has been released in production. So there are many techniques announced in the literature about this incredibly, how can I say, intelligent way of crafting examples that will interfere either with the training or with the inference of the model. Crafting also requires intelligence and time on the part of the attacker. The attacker is not just generating noise. It is generating a specific example which will either compromise the training or will interfere with the plasticity, the update of the model in production. And in order to do so, it has also to have an estimate of the internal operation of the model it's going to attack. It is easy to perturbate generating noise, but the generated noise is not really effective in compromising or interfering with the training or the inference of the model. You need to craft it. And the crafting is more a science, an art than a science even today. Definitely, generically speaking, the perturbator, this is the technical name for an example that has been crafted to compromise either training or inference. The perturbators are normal proposed strategies. One of the strategies is to make the perturbator close to the separation surface of the model it's going to attack. You see here the first row that there is a 7 which has been concocted from a tree, and basically this 7 digit this is the MNIST, very well known data set from the literature, and the attacker is supposed to know where the position of respect to the separation surfaces between the class of 3 and the class of 7, and the attacker is concocting a 7 that actually is closer to a 3. So it looks the 7 to a human eye, but it will be misclassified. So this is one strategy, and it works with certain data sets. There are other strategies that require an even deeper knowledge of the model. So you need to know the model you're attacking. You need to know how basically it is mathematically training, how the gradient needed to train it is computed during the training phase. And you will concoct examples that are orthogonal to the gradient. And in that way, you're trying to maximize the impact of your attack on the specific training. So here you see, for example, the image is showing that some examples, the examples that you see there, are orthogonal to the gradient, which is computed during the training of a model. And these examples have been concocted, while the noise examples, which are randomly oriented in the space, they are not maximizing their impact. So you would need a lot of noise to replicate the effect of a single orthogonal perturbator. So the attacker also needs to know the model well and needs to have computational power in order to concoct the example. So you could think, what can we do to defend ourselves? And I don't want to waste your time. Of course, there are many approaches to defend ourselves from this type of attacks. In our project, we use ensemble learning, and we design ensembles that are less sensible to this type of attacks than an original monolithic model, while not being less accurate than this one. So this makes it difficult for the attacker with a limited budget, because he could allocate enough computational power maybe to attack a monolithic model, but attacking the ensemble is going to be harder. This is our hope, at least. And of course, you can do that by creating this robust ensemble by partitioning intelligently the training data in such a way to make harder the work of the attacker. But you also have to keep in mind that you don't want to compromise the accuracy of your own model. Now, before I wanted to go to the end of this talk by asking a provocative question. We like all, the community, we all like to work on this type of projects. How can we make our machine learning models used in security robust with respect to attacks of someone who's trying to basically disable these models as they are deployed for protection? Now, is the attacker going to oblige? Is the attacker going to try to generate perturbators and interfere with the training phase? Or is the attacker going to focus on something else? Because of course, attackers, they tended to attack not for the sake of humiliating the researchers that design defenses, they tend to attack to achieve a goal. And so they may go for the point of less resistance. So in order to understand what are the countermeasures and whether we should invest or not on technique for making the training more robust or the inference phase more robust, we need some sort of a methodology to understand if, when, and how the type of countermeasure that I mentioned at the beginning should actually be the ones that I need to apply. And I need to do that not on an abstract definition of the ML model that I want to secure. I need to do this on a concrete instance of the AI pipeline where that model will be incarnated at production at runtime. So this is also our concern in this project. We don't want to concoct the best possible way to make a model robust just for the sake of countering an attack which is in the literature. We wanted to know which is the countermeasure that we should actually deploy in a given scenario, which is a concrete AI pipeline. And in order to do that, we refer to you see on the right on this slide of the life cycle of a machine learning model deployment, where, of course, the training is one side, just one stage. And there are other. So with ENISA, which is the European Agency for Network Security, we worked in a working group in which we decomposed the AI life cycle in fine-grained stages. You see these. And for each of these stages, our idea was to identify the failure modes for this stage and the countermeasures, the threats, and the countermeasures to alleviate those threats. So the given AI pipeline may be some of those steps, some of those stages are already secure for some reason independently. For example, the training takes place on a trusted platform, and I don't want to waste my time to create the ensemble that I mentioned before and my resources just to make the model robust with respect to training, because the training stage is not my weak point in that particular incarnation. So basically, we start from the notion of AI pipelines, and which are different from each other, even when they use the same models. So I don't want now to go into the details of this because we don't have time. But our main conviction is that we need the palette of techniques to make the models robust, and we need the methodology to decide if and when those techniques should be deployed in a specific pipeline. And this is an example of a pipeline that you see, which is actually a process built on top of the machine learning life cycle that I showed you before. So from the point of view of the pipeline designer, we are not interested in theoretical countermeasures. We are interested in countermeasures mapped to threats on a specific given pipeline. And so we do basically need a methodology that the security expert can apply. The security expert needed to identify the concrete pipeline, to identify the stages of the pipeline that may be subject to attacks, to select and detect the threats associated to the stages, and to deploy the countermeasures. So those countermeasures may be or may not be specifically addressing the robustness in training that I mentioned at the beginning. So this is the steps of the methodology that everybody applies, everybody uses to do threat modeling. And in the case of AI, the notion is that the architecture that we're going to look at is the AI pipeline. And the decomposition is the decomposition of that pipeline into stages. So basically, this is the work we've been doing with ENISA. This is an example of the assets for each stage of the pipeline that we use in order to identify the threats to those assets. And of course, some of those will be the data. And the data threats are the ones, for example, in the injection of perturbators. But you may have other threats that have nothing to do with the specific training phase that we mentioned at the beginning. So here it is an asset to threats map. Basically means that finding for each asset how it could fail to deliver what it is expected to deliver in the AI pipeline stage it is used in. And of course, in these from these threats, we will basically, from these threats you see here, we will basically identify the countermeasures. So this one is a simple pipeline that actually comes from a real examples from a European project, but I don't want now to enter into the details. You see, we have identified the assets in this pipeline. This has to do with the short-term optimization of the production of energy in small plants for energy production in the UK. So here we identify the assets from which could be attacked, and from each asset we identify the failure mode, and from the failure mode we associate a threat, and the threat we generate the countermeasure. Of course, we only handle threats which are known to be referable to a specific asset in a pipeline. We don't deal with unknown unknowns here. And of course, this is a problem, but at least from the compliance point of view, we can make sure that the liability angle is addressed. So identifying the threats, we are using an adaptation of the methodology proposed originally by Microsoft. It's called STRIDE. We call it STRIDE AI. And if you are interested, there is a GitHub site. You can find examples and all the material for applying this methodology to a generic AI pipeline.
Ernesto, you have 1 more minute. Sorry, just
Okay, but I'm there. Okay, so the methodology, of course, does not only identify the threats, it decomposes them, and for each of the atomic element in a threat will identify the basically the corresponding countermeasure, which may or may not be the countermeasure for making the training robust that I explored at the beginning. Okay, so this is all. Our technique is being tried out on a number of concrete pipelines in a number of verticals of interest, and we are specifically targeting energy, transportation, and healthcare. These are the 3 types of verticals that our project is targeting. And of course, I hope that some of those who listen to this this morning are interested to take a closer look at the methodology, to take a closer look at our compiler, and we will be, of course, open to interchange and discussion with everyone. Thank you very much for listening this morning.
Professor, just a quick question. Given all the threats that you mentioned, do you still think it's worthwhile integrating AI into the pipeline?
Yeah, so some of the threats that were mentioned basically are threats which are specific to attacks to the machine learning models in training and in inference. There are other threats. For example, sensor spoofing during inference is a threat which is documented in the field. So some of those threats are not documented in the wild as we speak. Others, which are maybe less attractive for the researchers, are. So this is why we want to try to do both. We want to try to address those type of threats that we, for the moment, are only addressable in the lab, but are fancy. But we also wanted to provide a concrete way to address those threats which are not documented in the lab too much, but are actually have been found in the wild, like sensor spoofing during the ML inference, which is well documented in a number of verticals.
Okay. Thank you very much, Professor. It was very interesting. I think the next session is recorded, right? Okay, so next session, we have a recorded session from Raluca Adapopa. She's an assistant professor, US Berkeley co-founder and president of the OPIC Systems.
Hello, everyone. I'm Raluca. I'm a faculty of computer science specializing in security at UC Berkeley, where I work in the area of privacy-preserving computation and secure computation. I'm also co-founder and president of OPIC System, which commercializes technology for privacy-preserving computation. Today, I'm going to tell you about the open source we've been developing in my group at UC Berkeley called MC Squared, which enables learning on confidential data that no one can see. Let me give you the abstract problem it's trying to solve, although this problem shows up in many instances. Organizations often wish to learn from data from multiple organizations, but they cannot share it because it's confidential or because there are privacy regulations and whatnot. Here's one specific example from money laundering. Criminals often hide their traces by doing money laundering across different banks. And the banks would like to detect this money laundering because they're losing a lot of money every year to money laundering. But because the criminals are hiding their traces across the different banks, any one bank alone has a really hard time detecting these criminals by looking only at its data. This is why the banks would really like to put all this data together and start identifying the loops, transactions that these criminals make. It becomes much, much easier to detect them that way. However, the problem is that the banks are in competition, so they can't share data with each other, or there are privacy regulations and issues like that, which basically prevents them from putting their data together and finding these criminals. Now, this quote from the Chief Risk Officer of Scotiabank, and we're collaborating with Scotiabank on this use case, says that if they were able to put together their data and jointly perform money laundering, they would detect such attacks, such criminals, by orders of magnitude more efficiently. So they really need the technology like that. Besides this, the need to collaborate with confidential data that people cannot see shows up in many other cases, in many other financial cases, such as fraud and human trafficking detection through financial forensics, or flu prediction or cancer diagnosis, and so many other cases. This is why my students and I at UC Berkeley have been developing the MC Squared platform, which stands for Multi-Party Confidential Computing. So MC Squared enables organizations to learn on confidential data from different organizations without showing it to each other. And this is open source that you can play with. And basically, the technology embodies the principle of sharing without showing the data. So you can use MC Squared either in the cloud just for your own data to protect the data from the cloud or from hackers, or you can use it to collaborate across your different divisions or branches that can share data with each other, or you can use it to collaborate with a whole other organization whenever you need to learn from data that some parties cannot see. So how does MC Squared actually work? And I won't go into a lot of technical detail, but I'll just give you a very, very high-level overview. Currently, in doing this kind of privacy-preserving computation, there are two main state-of-the-art technologies. One is purely cryptographic, such as you might have heard of secure multi-party computation or homomorphic encryption, and the other leverages recent hardware advances like hardware enclaves. And my students and I have done a lot of research over the past bunch of years on each one of these technologies because they have a trade-off. The cryptographic approach is cleaner from a mathematical standpoint and it doesn't need specialized hardware. but it's very slow still. You can use it for simple computations like averages or counts, but you can't yet use it for the kind of realistic machine learning training people do today or rich SQL analytics. Hadoop enclaves, on the other hand, are much, much more efficient. So in the rest of this talk, I'm going to focus on Hadoop enclaves and the technology that we built using them. So let me tell you what Hadoop enclaves are at a high level. They're basically isolated execution environments that is enforced by the hardware. So they protect against an attacker that has root access on the machine or compromised operating system, because that attacker is only going to see encrypted data. Basically, deep down in the processor, under the die, there is an engine called ME, which is a memory encryption engine. So it encrypts all the data going out of the processor into main memory. So if an attacker has access to the operating system or has administrative privilege, the attacker can try to peek into memory, but it's encrypted. Now, whenever the data comes back into the processor, this ME can decrypt it so that the core can compute on the regular data, unencrypted data. And this is why it's very, very fast. Okay, so it's fast because you can compute on regular data inside the processor, but it also provides strong security because to any software on the machine, main memory is encrypted. The nice thing about Hadoop enclaves is that these days they are available on public cloud. So this is a very timely technology. For example, Azure has Azure Confidential Computing, in which they provide a public cloud with this kind of Hadoop enclaves. Hadoop enclaves do have a downside, and that is the side channels, which are indirect ways of information leaking. However, there's a lot of research into how to protect against those, and a lot of my research and my students' research is dedicated to protecting against those side channels. So a lot of MC² is incorporated in those mechanisms and protects against a very large class of side channels. So let me give you an example of how one can perform machine learning on confidential data using MC². And let's say we have a bank here from the anti-money laundering example. Now the bank is going to run the MC² client, the client software. And the bank also has, as part of this client, is going to generate a key with which its data will be encrypted. Now on the cloud side, we have a deployment of MC² with enclaves. So now the first thing that the bank does is going to have to check that these enclaves are being set up correctly. And this procedure is called remote attestation, and it's a very nice property of Hadoop enclaves. It enables a remote party like the bank in this case to verify what's running on the enclaves in the cloud. So the bank can actually check that the desired software is running on those enclaves. For example, the desired anti-money laundering learning software, but nothing else. There's nothing else. There's no malware or nothing else, right? There's exactly the software that the bank intends to run. That's what's going to run on the enclave on the bank's data and nothing else. So now after this remote attestation procedure happened, which involves actually hardware mechanisms on the enclave side. But after this remote attestation procedure verified, the bank can exchange its key with the enclaves over a secure channel. So now the enclave, if it receives data encrypted from the bank, it can decrypt it and compute on it. All right. So now our bank is going to take some data, encrypt it, maybe store it in the cloud encrypted or load it encrypted from the cloud. But the point is that it's going to be loaded into the enclaves, and the enclaves can decrypt this data because they have the key of the bank. Now the enclaves can compute on this data, some training script, let's say, provided by the bank. Okay, and they're going to compute on the data deep inside the processor is decrypted. But to any outside party, to any software attacker, it looks encrypted. And then they're going to produce the results. The results are going to come out of the enclave encrypted because everything comes out of the enclave encrypted. And then the results are being sent to the bank, and the bank can decrypt them and enjoy them. So now, what happens if we have multiple banks that want to collaborate with each other? It's very similar. The banks each are going to have their own key. They each are going to verify the deployment of enclaves in the cloud, send their encrypted data with their encrypted key, so the enclaves can compute on the data from all the banks and compute some aggregate results, for example, suspicious anti-money launderers. And then these results are encrypted under everyone's keys and returned to the banks who can enjoy the results. All right, so I'm going to show you a demo of how MC² works on the example of anti-money laundering, and I'm going to take it step by step from the command line so you can really see what's happening inside the system. But of course, if one uses MC², it doesn't show to the client all these details, right? It's easy to use. It's much more abstracted out. But here I want to show you step by step what's happening so that you can really, get a deeper understanding of the system. All right, so in this demo, we're going to have the MC² client installed on the premise of a bank. Also, we're going to have a deployment of MC² on Azure cluster, in this case, Azure Confidential Computing. On the top screen, you're going to see the inner workings of the client machine and the output and what it does on the client side. And on the bottom screens, you're going to see the inner workings of the cloud side. So the virtual machines with hardware enclaves belonging to MC² in the cloud. Now, again, this is going to be command line, but all of these details will be abstracted out in 3 simple steps in the actual open source. Okay, so first the client is going to encrypt the data and upload it. Then the client is going to attest that MC² is deployed properly on the server side. After that, the cloud is going to train the model, and then the client is going to download the results and decrypt them. Okay, so now we begin the demo. So on the client side, we have some data. This is some synthetic data we obtained from Scotiabank. Let's take a look at it. We're going to use this data for training. So it has a customer ID on every row and some synthetic transactions that this customer made. And so we're going to use this data to train a money laundering model. And then we're going to use it to perform predictions for money launderers. So we have also testing data that looks very similar. Okay, so now on the client side, we're going to encrypt the training data and testing data. And we're going to upload both of those to the cloud. So let's take a look. This is the encrypted data. It looks like gibberish. It's random, it's encrypted. Now we're going to transfer this to the cloud, both the training data and the testing data. So let's try to visualize the data on the cloud and see how it looks like. And it's encrypted, right? Because the server, the cloud, is only going to see encrypted data. All right. So now back on the client, we're going to have to prepare the training script. Well, for that, we're going to start with just a regular data science training script, let's say in this case for decision trees. And this is just a regular script a data scientist would write with no expertise of MC² or confidential computing whatsoever. Then to make this run in a privacy preserving way with MC², one just adds basically MC² and initializes it. Just a few lines of change, that's it, but no actual change to the actual training script. So it's very easy to use. All right, now we're going to start the cluster on the server side. You're going to see some output on the first VM. You'll see what the VM is doing. And on the other VMs, I'm not going to have any output, but using the htop command, we can see when they are utilized. All right, so back on the client, the first thing we're going to do is we have to deploy this script on the VMs in the cloud, but first we're going to run the remote attestation procedure to check the environment at the enclaves. The check proceeded successfully, so as a result, the servers, the cloud, are starting to train. They're loading encrypted data, they're encrypting it deep inside the enclaves, processing, and you can see that the VMs are utilized. So outcomes in the cloud, the trained model and predictions, we can try to visualize them. So we can see that the prediction results are also encrypted because always on the cloud, everything will be encrypted. The attacker of a cloud cannot see the data, it's all encrypted. But on the client side, we can download these results and we can decrypt them. So here we can actually view which customers are believed to be launderers and with what probability they are believed to perform money laundering. Okay, so hopefully this demo gave you a sense of step-by-step of how MC Squared works. We wanted to take the MC Squared open source further from instead of just being an open source artifact that's based on research artifact, to make it into something that's easy to use, something that one can rely on, something that has full-time support and is efficient. So that's why some of my students and I and colleagues, we started a company called Opaque, which does exactly this. Packages MC Squared into a very easy to use, robust, very functional and efficient system. This is the team behind Opaque. It's 3 of my students, 2 of them graduated with PhD and 1 with master's, experts in this area, and my colleague Jon Stojka. So as part of Opaque, we provide 3 modules: machine learning in a confidential way, federated learning in a confidential way, and analytics in a confidential way. And these are running on top of major cloud providers like Azure. The nice thing is that we've already had a bunch of adoption, either in production already or internally at a number of companies. All right, so in conclusion, Opaque enables machine learning on encrypted data using our open source technology MC Squared that we developed in research over multiple years. It's open source, you can freely play with it, give us feedback, let us know if you have any use cases, if you would like to collaborate or if you'd like to use the system for any of these, please go ahead and contact us and we would be happy to work with you on helping you adopt MC Squared. Thank you. Any use cases, if you would like to collaborate or if you'd like to use the system for any of these, please go ahead and contact us and we would be happy to work with you on helping you adopt MC Squared. Thank you.
Thank you very much. Luca, it was very interesting. As I said before, this is an area that we are also experimenting with, even though not on an enclave solution, but on we're working with full homomorphic encryption. But I'll be sure to be in touch with you because it sounds very interesting. One question I have for you is, what do you think the greatest challenge is in making this a commodity, something available, working for everyone?
Yeah. Thank you for the question. It's a very good question. I think The biggest challenge is regulations, right? So a lot of companies have confidential data they cannot share, and they would benefit from doing this kind of privacy preserving computation learning. But regulation is a big hurdle because companies across different countries or in markets like financial or medical, they have to comply with very strict regulations. So we need to make the regulatory bodies understand enclaves and cryptography, right? And enable these kind of technologies to be compliant. So that's, I would say, a slow process, and it's one of the biggest challenges in my opinion.
Thank you very much. We're going to move to the next session. We're going to have it with Roy Schuster, who is a researcher from Tel Aviv University. It's going to be an online one. Roy is in New York, right? So he got up really early for this.
So this talk is about resilient machine learning, or kind of my perspective on it. And it starts with the observation that we are having more and more machine learning in software in general. And it's replacing existing software components and also helping some new ones develop. And we are trying to ask how does this affect, the security and privacy of these systems? And ML has some inherent problems, issues that might raise, security problems. The first one is that it typically has a lot less guarantees about robustness guarantees than traditional algorithms. And here there's a few examples. The well-known example of adversarial inputs, as they're called, is one of those. And it stems from the fact that ML is optimized for low mean error, but attackers can always try to find pathological worst-case inputs. Now, the second problem, which I'm going to focus on much more in this talk, is that ML it increases the information flow between mutually distrusting entities. So if we have this is a comparison between a classic algorithm that just has an input and output, the algorithm we teach in algorithms class, for undergrads, and this is a machine learning algorithm. Now, they don't look that different. Machine learning algorithm only has an additional training phase. This is a very simple supervised learning, for example. But this training phase does add some complexity, because what if the training data is private, but then the output of the model goes to some public place? Or what if the training data comes from some untrusted source, but the output is trusted for some important decision? So there's also the issue of training by third parties, which can also affect the trust in our model. And so this has problems. But when we deal with more complex models that are not just don't have just one training procedure, not just a classical supervised learning scenario, then we might have a much more complex situation. And if I try to paint these red and blue boxes that I did on the previous slide, on these cases, one is for transfer learning that has two training procedures, and one is for a more realistic data pipeline that might be used in the real world, then it would be very, very, you would see arrows going everywhere in red and blue boxes, and it would look very scary. So there are two types of problems that are arising from these added information flows. One is that secrets can leak to unauthorized parties, and the other is that untrusted data can be used to make decisions that we then trust. I'm going to refer to these problems as leakage and poisoning, and I'm going to give examples of this from our work. So the first example is the first case study, let's say, is an example of leakage. And it's a work by Jian Sun and Vitaly Shmalikov and myself. And it's about de-anonymizing text by fingerprinting language generation. And the point here that we're arguing for is that ML building blocks are security hotspots. They are coded ones, they are programmed ones, but then they are used multiple times by multiple downstream models, which we can see here. And for many, many tasks, every one of these models is actually used many times too. And so we really want to get it right when we are implementing these building blocks that are used to build these models. And they do, of course, operate on sensitive data. So we also want them to be secure. If we program them in an insecure way, if we implement them in an insecure way, they might leak our secrets to third parties. And in this work, we took a case study of an algorithm called nucleus sampling. That's a building block for NLP. It helps for natural language processing. It is a method used to sample the next word when we are generating language. For example, GPT-3 generates language, probably using some similar method, but maybe even using actual nucleus sampling. But nucleus sampling is considered a very good method to sample the next word when we are completing text and generating text. And we found that when we use nucleus sampling, the series of what we call nucleus sizes, there is a nucleus size element in that algorithm, and the series of nucleus sizes is actually uniquely identifying for the text that we are generating or that we are auto-completing. And why is this bad? This is just, the nucleus size is just an internal artifact of the algorithm, but apparently due to some implementation detail, the nucleus size can be snooped by an adversary that is co-existing on the same machine as a machine doing text generation or auto-completion using some GPT-like model. And so that means that, that if we have an artifact that uniquely identifies texts and it leaks to third parties via this side channel, because of the implementation detail that basically makes it leak. It leaks through the cache side channel. I'm not going to get into what that is, but it does. So given the text in the side channel trace, we can tell if the text was typed on the victim's machine. So the kind of takeaway here is that due to some implementation detail that is very natural to have when you implement nucleus sampling, the identity of your text basically leaks, or where the content of your text basically leaks to third parties who are unauthorized to view it, or could leak to third parties who are unauthorized to view it. And this can be mitigated, I won't say easily, but it's in a straightforward way we can mitigate this in a very meaningful sense. And all we need to do is apply some different flowed arithmetics, and it's completely standard techniques. But we do need to be aware of it when we are implementing ML building blocks, and that is the main thing that we are trying to argue for, that ML building blocks are kind of new to us in a sense that their programming practices are not entirely mature, and we want to get it right, and we want to mind even things like side channels and security when we are programming these ML building blocks that are then used all over the world. So if we did that here, that would have prevented this leak. And going forward, we would like practitioners to do that. So this was a case study of leakage. And again, this talk started by saying that there's two problems, leakage and poisoning. Now I'm going to show two examples for poisoning. So the first example is what happens if we have transfer learning. So we have two phases of training. So we have pre-training and then fine-tuning and then inference. Now, in pre-training, data might come from untrusted sources. And in order for that data to affect the important decisions that our model is making, the changes that the untrusted sources would have to go through 2 training procedures and then inference. So it seems kind of indirect, and it seems like maybe attackers who can only affect the training data of the first training procedure, maybe they can't really affect the decisions of the model, the decisions that the model is making. But this is what our research Humpty Dumpty is about. Research with Tal Schuster, Yoav Meri, and Vitaly Shmatikov. And it's about how we can change word meanings, which is kind of an old idea, to change word meanings to do harm. And what does it mean in NLP or in machine learning? So word meanings are encoded in a low-dimensional vector space. They are encoded once, and then they're initialized once and then used multiple times for many downstream task solvers. And if our adversary, let's call them Humpty Dumpty, would want to make ignorance mean strength, as in the George Orwell novel, then they could maybe potentially make a change to the corpus that the embeddings are learned from. And by making this change, maybe they can cause this targeted notification to happen in the embeddings. Because again, the embeddings are learned from a specific corpus that is open and that can be changed, like Wikipedia or Twitter. But the challenge that this research was trying to tackle was, what should we add to the corpus in order to do that? And it's not simple, because there is an unclear correspondence between the word meanings as they are encoded by the embedding and the training corpus features. So, but in this research, we did find the connection between the embedding space and the concurrent space. So our adversary could define what they want to happen in the embedding space and then express it in terms of the concurrent space, which is statistics over the corpus. And then they could derive what corpus changes they wanted to make. And the summary of our results, that we can attack downstream tasks, so we can attack all the way from, changing word meanings and then making a word-to-word translation system fail because of that. And we can attack a named entity recognizer and resume search engine. The attacks can be stealthy. They can't be avoided by standard techniques, and they transfer across algorithms, data sets, etc. Another example, which is kind of very highly relevant for this past few weeks, discussions, is a paper about vulnerabilities of autocompletion system, and specifically code autocompletion systems. So we know that that language models and AI can complete our text, which is great, and with code, as we've learned in the past few weeks with GitHub Copilot, it can actually be really, really useful, because they can save us the need to be very intimately familiar with the API that we are using. So, but these auto-completion models, of course, they have privacy issues, which have been discussed a little more, but this is a different issue that I'm going to talk about, which is that in order to train these these code auto-completion models, we need to train from a big open source corpus, such as Wikipedia for text, for natural language text, but here we would train on open source repositories. And open source developers can be anybody. They can be you and me, but they can also be malicious. And so if the developers of the code that we train on are malicious, then that might be that they can actually make our model behave in some malicious ways. Now, what malicious ways could our auto-completion model, such as GitHub Copilot, not specifically, but such as GitHub Copilot, behave in? So, for example, think about this developer in Huli Software headquarters, and they are using their IDE, and it has an auto-completion model. and they're trying to choose encryption modes. Now, all they want to do is go home because it's late at night, but they have to choose encryption modes right now. And their auto-completion model is telling them with 99% confidence, it's fine, you can choose ECB. Now, ECB is very horrible, and you should never choose that when you're choosing encryption mode, but the developer's own IDE is telling them to do that. So we think that they will take this bait and choose it. Now, this attack that we mounted successfully, we could also do it in a targeted way so that it will only affect specific developers and specific corporations. So this looks kind of dangerous for code auto-completion systems that, again, have to train on a lot of untrusted data. These are results. I'm going to skip a little bit on the numbers because there's a lot of numbers, but qualitatively, the attack works, and it works in a targeted way. And we can target individuals and specific code repositories, and so this is kind of cool because it's a very relevant attack on a system that has been recently very hyped. So I guess that's my takeaway here. So I've covered leakage and poisoning, and I want to end on a slightly more positive note of what can we do about all of these problems. So we could try to apply, there are known defenses against poisoning, but the problem is that they are expensive and we can't just apply them everywhere. That's just not going to work. So we could try to maybe only protect in dangerous scenarios. Maybe if we could identify that here there is training data that comes from some untrusted source and it goes to some trusted output, then maybe we can just protect this pre-training procedure and then everything in our pipeline as well. But how do we even tell that this pre-training procedure can be protected and that this is the point that we need, the hotspot that we need to protect? There's currently no way to do this. So, but there are traditional ways from systems security literature to do exactly these sorts of things, to surface points of failure and points where we should be more aware of, and try to compartmentalize software and apply some traditional access control techniques in order to do exactly that. So there is hope that maybe in the future, in the near future, we will come up with some better ways to deploy these defenses and protect against these attacks. So that's it. That's my talk.
Thank you very much, Roy. One question after seeing all this, if I'm an organization and I'm about to train, design, or deploy an algorithm, what would you suggest for me to do in order to mitigate this kind of risk?
So right now, I would say that it's very hard to avoid having some sort of expert. If you have a sensitive scenario where you have sensitive data, or you have a sensitive, or you're trusting your model to make poor decisions, and it's very hard to avoid having an expert review your design decisions with information flow vulnerabilities in mind. Is unfortunately the case right now. Yeah.
Okay. Thank you. This concludes our session.
Excellent.
Thank you very much, and have a good time in New York.
Thank you.